As mentioned, our presenter today is Jeff Langford. Jeff is a senior analyst and manager of International Group of Analysts here at Fluke. With over 2 decades of experience in predictive maintenance, Jeff holds a Cat 3 vibration certification and is also certified in infrared thermography. Currently, Jeff manages a global team of analysts and has extensive experience in leading vibration program startups and conducting infrared surveys, particularly in electrical inspections. His expertise also includes fan balancing with additional skills in laser alignment. All right, everyone, you're here for the evolving landscape of vibration analysis. Jeff, take it away.
Thank you, Robin. Yeah, as Robin mentioned, just a quick little recap about myself. Over 25 years of experience. I joined Azima in 2008, initially as an analyst, promoted up to a manager level. My current responsibilities, I help lead our remote vibration services team and help drive our automated analytics on a daily basis. Just a quick overview of our company, kind of where we came from. DLI Engineering was founded back in 1966. Azima was formed in 2005. In 2008, Azima purchased DLI Engineering. It became Azima DLI. Of course, that then gave us our own hardware software. And then, of course, in August of 2023, we were acquired by Fluke. We became, Azima DLI, the Fluke Reliability Company. And currently today, we're, poised reviewing 1 million plus analysis reports, machine test reviews per year. So kind of a quick historical process of, how we got to where we are today and how we want to relay our lessons learned out to other customers and maybe, kind of enlighten you to maybe look for better solutions or whatnot. But prior to 2010, the services approach by Azima was pretty much the same as anybody and everybody else. We offered diagnostics as a service, but our technicians would travel to the customer sites, collect vibration data on a monthly basis, typically, just a traditional walk-around program. The analysis and reporting were then performed manually. It's always been my observation of it's about a 1-to-1 ratio of every hour that you spend in the field collecting data. It's about an hour of manual analysis and reporting to document those and to find any faults and document and report those. After 2010, we here at Azima DLI, we kind of transitioned to a remote analytics role, and we termed that Watchman Services. DLI had previously deployed this with the U.S. Navy as well as some other clients. But what we were looking here to do was eliminate the need for travel. We did that by enabling the site personnel to collect their own data. We would go out and set up the databases, train the customer sites how to use the data collector, how to collect that data, and how to transfer it. Initially, that data was transferred via a secure portal using predefined routes. Our data, we used a lot of other data collectors back in the day, and most of it all was, route-based data collection. DLI had utilized replication-based data transfer, and that fit our model exactly of what we were wanting to do. So that eliminated the uploading and downloading of routes. The data collector houses the database. You simply go out, collect your data. That replication process sends us a copy of that data. Very easy, user-friendly process. And with our integrated Expert Alert software, we rely on the automated results and the rule-based software for analytical screening of the data. So typically, historically, you always want to do a diagnostic targeted approach, which basically means you simply do full manual analysis on all vibration data. You look at everything, the spectrum, the time waveforms, the trends, the overalls. You're scrutinizing that data. It's very high value, but it's low volume. A really good analyst, a very experienced analyst can, do really good assessments. but that gives you a lot of resource constraints. Um, Typically, with data collection, you're only looking at, a decent analyst is looking at, 25, 30 machines per day per analyst. The benefit of that is you typically find faults a lot earlier on your PF curve because you're manually reviewing this data. You're looking for, uh, you know, basically pattern recognition in the data. You're looking for non-synchronous content, uh, looseness, harmonics, things like that. But you're typically looking at that pretty early in the PF curve. The alarming approach in the past has also um, been a technique that a lot of people have relied on. You typically base everything off of just general overall vibration alarms. The the value there, well, it's low value but high volume. Um, you're screening a ton of data through a system that will simply give you an alarm. It's not typically not diagnostic in nature. Does not give you any actionable results. It typically only serves as a hand raiser. Um, so then you would oftentimes have to then go collect additional vibration data for diagnostics. And by that point, oftentimes once it reaches an alarm threshold, you're in a late stage reactive mode, much further along the PF curve. So that is a little more risky, letting faults get to that later stage before you identify them. Let's talk just a little bit for a second about wireless sensor technology. Not all wireless sensors are created equal. Some collect diagnostic data such as time waveform, spectrum, temperature, other trendable parameters. Um, Other wireless sensors often only take overall values. They simply act as a hand raiser with no diagnostic recommendations, as I mentioned earlier. Um, so I kind of warn um, customers to use caution. Make sure that you're getting what you think you're getting when you look at going into a wireless program, because they're not all created equal. The um, the evolution of the technology does not equal the evolution of analysis. The more data, more machines and more data does typically means less analyst capacity. So more data doesn't necessarily equal better analytics. Um, the problem there is typically overrun of the analyst. So getting data more frequently does not necessarily mean better analysis. It typically would give you an earlier indication of a fault, and you can trend that fault, but you still got to do something with that data. And when using a hand raiser or alarm only type method, you're simplifying your results at the detriment of risk. I said you're going to be much further along on that PF curve and potential fault failures and things because you're detecting it much later. And also, it makes it harder to retain experienced staff due to overload or missed failures. What I mean by that is, if you've got an excessive amount of data to look at, a person can only do so much in a day as far as diagnostic analytics. And if they're not looking at the data, it's a pretty good chance that they're going to miss something. There's going to be a failure that was not identified. Then that's going to reflect poorly on the analyst, and then the analyst is just not going to, want to be responsible for these missed opportunities and missed things. Going into a little bit of detail here about the wireless data tsunami. As I mentioned a minute ago, more data does not necessarily equal better insights. It often leads to analyst overrun. It's ineffective use of high value talent because you're significantly restrained by your resources. You're typically looking at 30 to 100 times more data by switching to wireless. And typically overall vibration is not enough of a diagnostic. You might get an alert, but what's your fault? There are, of course, band alarms or certain things that you can do, but we're talking about, in this scenario, the absolute simplest of a wireless system that would pretty much only give you an alarm. A better approach would be to refocus the analyst on actual faults. we've studied data for years, and what we refer to as fault rate, which is pretty standard across industry. About 10% of the data that comes in is an emergent fault, which we would define as a moderate. And then serious and actionable faults is about 3% of the data that we see come in. So we automate our low risk results and we escalate those high risk directly to an analyst. So we typically only look at, the actual true actionable faults. The example here in the center of your screen is a actual customer that we partnered with. It's a refinery that has 1,600 machines in their walk-around program, a traditional walk-around program. They have six embedded analysts there on site. And when they were doing their traditional walk-around program, they were looking at about 19,200 some odd machine tests per year. Do the math there, divide that out. That was about 3,200 machine tests per analyst that they were looking at. Like I said, doing manual analysis. Pretty easy work, or pretty sustainable workload. I don't know if it's an easy workload, but pretty sustainable workload. So they made the decision to switch over to some wireless sensors. So they went out and put wireless sensors on these 1,600 machines. Well, that gave them, from instead of monthly data, now they're getting daily data on 1,600 machines. So that increased their workload by 30 times. So, pretty sure the site, we're not willing to go out and hire 30 times more analysts to handle that workload. So the analysts were absolutely overwhelmed. Now they're looking at 584,000 machine tests a year. Do the math, that would be 97,000 each. This absolute analyst overload. So they were drowning in data. They could not process all this data. They could not manually review this data. They needed some help. So they reached out to us, and we were able to offer this customer some assistance using our automation. Kind of going back in time here a little bit, 2022, back to the timeline I showed earlier, we implemented the Treon wireless sensor in our services offerings back in late 2021. And it was kind of a slow rollout. It didn't get a lot of traction as quickly as was anticipated, which actually was a little bit of a good thing because it gave us an opportunity to be able to respond and prepare for this flood of wireless data. But back in early 2022, we were averaging about 250,000 machine tests per year. By 2023, we had rolled out, a significant number of the wireless sensors to our customer base, and that was why you see that pretty substantial jump there in 2023 in data. 2024, we fell just short of 1 million machine test reviews. This is kind of a different presentation of that, but this year current projection is probably hit somewhere around 1.7 million machine tests, and with continued growth and what we're looking at today is we're looking at probably 3 million plus machine tests by next year, end of year next year. What gave us the ability to handle this amount of data that we process is our automation. This chart here shows, I said, back in 2022, our rule base pre-screens the data. Our analysts review that data, and we've always had a lot of trust in our system. Once we have a certain amount of data and averages and things like that, we very much trust the process. We trust the analytical results that we get out of our automated software. However, it was still a matter of reviewing those machines. Those machines still had to be signed off on. So we implemented a process of automation with some external tools that allowed us the ability to automatically review those machines and offer those diagnostic results back out to the customer without human interaction with that data on a regular basis. And back in 2022, you can see here the blue is our data inflow. The orange is the amount of that data that was automated. probably back in 2022, probably a third or less of our data was automated. By 2023, we had hit about the 50% mark. 2024, we were hitting about 75, 80%. In 2025 year to date, we're running nearly 90% of our data that comes in gets automatically reviewed. So how have we been successful doing this? We have a dedicated workflow tool that assigns this workflow out to our analyst. It's a specialized tool that was developed specifically for us. But our delivery process is driven by severity. We call that an SLA, a service level agreement, our contracts with our customers. We handle different severity differently. That can mean, if we have a machine test that comes in as a green or a slight, we can assign that service level agreement to maybe a five business day turnaround. It's low fault, low risk fault. Not much to worry about there. We can push that data off for 5 days, or we can completely automate that process. A moderate machine fault come in, we would set that to a 3 business day turnaround. But typically, your seriously extreme, we would want to elevate that or escalate that to an analyst rather quickly, get those results back into the customer's hands as quickly as possible. So we can set those SLAs as a 1 business day or 1 calendar day turnaround. Our current SLAs for all of our wireless data and integration data that we pull in is 24 hours. That data is reviewed, results are delivered within 24 hours of receiving that data, 365 days a year. Our team of analysts covers weekends and holidays, and like I said, we really rely heavily upon the automation process. But our diagnostic engine, our rule base, all that works together along with human analysts to generate those results out. Very impressed with where we are today and how quickly we've gotten to where we are. A lot of hard work, a lot of our development team has worked in the background to give us the tools and the ability that we have to do what we're doing today. This is a snippet of our workflow tool. Call it a virtual diagnostic center. Data flows in, it gets assigned out to the analyst by workload, what's due on a daily basis, and it's mixed SLAs. We have some that are we have a traditional walk around program data that comes in from our Trio systems, but even within that, there's different SLAs. It's 5 business days, 4 business days, 3 business days of how quickly we review that data. So this tool actually tracks the machine test by severity, by the SLA that's applied, and then assigns that out to an analyst with a due date. So our analysts spend a lot of time daily in this tool looking at what they need to be working on when it's due, how they need to where they need to focus their efforts. But kind of a quick introduction into our wireless systems. We refer to it as Watchman Air. As I mentioned, back in 2021, we partnered with Treon to use their wireless sensor. It is a triaxial MEM sensor with temperature. In the bottom of the mount here, there is a temperature probe. So these sensors take hourly scalar data. That includes velocity RMS, acceleration. We implement impact DMOD, so that takes impact DMOD levels hourly and temperature hourly. That data gets stored in the cloud once per day at a predetermined time. The spectral data gets transferred into our system for diagnostic results to be generated. So we're not looking at the hourly data, we're looking at daily data. But these are mesh networks, so sensor will talk to sensor to get a path out to the gateway. That data, I said, is then transferred from the gateway to the cloud. The gateway can either be Wi-Fi, LAN, or Ethernet, or cellular. We have a lot of success using the cellular network just because a lot of your IT requirements for getting data on an implant network is very restricted. So we seem to have a lot better success simply just bypassing the customer um, network and just use a cellular modem to pull that data out. But once that data is received, it's run through our expert alert diagnostic software, um, fully automated screening of the data. We have 6,000 plus rules, 1,200 plus component types with our statistical averaging applied to that data, assist with the screening process, and then those results are delivered back out to the customer via a user portal, which in this case is currently our predictive portal. We have made strides over the past few years to become pretty data agnostic. We are able to ingest data from a multitude of different platforms. Of course, our own Trio, our own online systems, of course, the Trion wireless sensor. And since we've been purchased by Fluke, we're working very closely with Prooftechnic. We're ingesting VibGuard data now at several sites, ingesting that data and processing it through our automated system. We also have partnered with National Instruments in the past, where we're using their hardware in conjunction with our software. But here lately, we have a number of customers that we are ingesting Bentley Ranger Pro data from, and that applying our rule base and our statistical averaging and algorithms to their data to make it manageable. Like I said earlier, we're removing the low priority faults and relying solely on automation to clear that data, and then escalating the more severe faults, the serious extremes, the risky faults up to an analyst for human review. But we're ingesting, like I said, data from multiple platforms. That data comes in our system, is screened. We have a lot of tools in the background, this data lake that you see here in the blue that talks about all the different components. We do have, the machine learning and AI that helps us to mature these machines very quickly. And those results are generated back out to the customer via our portals. We have a program management team that does meet with the customers periodically for renewals, and we touch base with the customer frequently to make sure their systems are working as expected. They're getting the results as expected. We have certain KPIs that we can pull in the background that identify as key saves, ROI, things like that. We work very closely with the customer to develop these KPIs and things that show what they're looking for. Program justification and things like that. So the key to our success is basically empowered vibration analytics. You've heard me mention statistical averaging. So what exactly is a statistical average? It's very, very narrow band alarming, if you will. A lot of your automated systems rely on band alarms or overall alarms and things like that. We use a little bit different approach with the AI, machine learning, and our statistical averaging. Basically, in this spectrum that you see up here at the top, it's kind of hard to see with as small as this is. But the dark blue is the actual raw data, raw spectral data. The red is our average. Of course, once you get multiple averages, you get some level of standard deviation. So if the data, and that defines the machine as good. Once we apply our averages, we've defined that machine as good. The next data set comes in. If it's within the average, then by default, it has to be good. No further screening is required, because if the data fits within the average, it has to be good, as we've set that known amplitudes and frequency content as being a good machine. But the diagnostic engine plus manual analysis gives us very high value and a very high volume. We're able to screen this data virtually instantly. The data comes into our system. Our expert alert software pre-screens the data, gives a diagnostic fault based upon that fault and severity. If it meets certain criteria for automation, then those results are delivered virtually instantly. If it is escalated to an analyst with a serious or extreme fault, then depending upon the SLA, that can be anywhere from, 1 calendar day up to, 5 business days. It just depends upon the SLA. But for our wireless, like I said, that data is analyzed every day. It's a 24-hour turnaround on data comes in every day of the year. We also generate very highly detailed, actionable results. So if a machine comes in a level of fault with a severity, it's very descriptive as to what the fault is and what the recommended action would be. If it's misalignment, then the recommendation is going to be to, perform an alignment, inspect the coupling. If there's looseness observed, the recommendation would be to inspect bearing fits, inspect for loose bolts, check for broken welds, things like that. But we focus our analysts on the actual faults, not the greens and slights. And it's very much a trusted assessment based upon our AI, machine learning, and historical processes. We very much trust our system and our process. And we typically find faults very early on the PF curve. Of course, we're looking at machine data. So, machine data doesn't always give you a very early indicator. Sometimes a fault develops very quickly. And we've seen that even in the wireless data that comes in where we're trending and tracking that daily. We've seen where data comes in one day and the machine's green. 24 hours later, we get the data and it's a serious bearing fault. That fault has developed that quickly. It doesn't happen a lot, but we do see it. We've seen it a number of times. There are other times that we see a very, very early fault develop, and we watch it and trend it over a period of time until it escalates to a level that, okay, now it's time to take some action. But our process here is very scalable. We can apply it to a customer with 10 machines or 10,000 machines. It's very scalable, very quick to get up to speed and get these results delivered out very, very quickly and efficiently. But the statistical average absolutely works. We deem a machine mature once we have at least 6 averages. We have a lot of criteria that we hold ourselves to a high standard. Certain amount of machine information must be known. A certain number of averages must be met in order for us to automate a machine. So we're not typically going to just take raw data and automate that process. We're absolutely going to spend some amount of time scrutinizing that data, using machine learning, using AI, using human analysts to ensure that data is applicable for automation. All machines don't fit the criteria to be automated. There's some machines out there that they're always going to require manual analysis. So we're able to differentiate those and put them in the right group for analysis. Kind of going a little bit more into statistical averaging. I said you have an overall alarm, which basically means if any content within that data reaches that alarm threshold, then you get an alert. It's not diagnostic in nature at all. You just simply say that you have an alert. So then you either have to go scrutinize that data. If you have spectral data, waveform data, things like that available for analysis, you have to go scrutinize that data. If the system that is in place that's only giving you an overall alarm does not have diagnostic data, then you would have to then go use some other instrument to go out into the field and collect that data for analysis. We kind of combine all that together. The statistical average is very discrete. We do have 8,000 line criteria screening for each machine. And we've got years and years worth of data that we're able to compare similar machines across industries out in that data lake. We have all this, so we pretty much know from experience and data what a certain type of machine should look like. The other thing here about this statistical averages, that is based on our MID, which is machine internal design template. So if you do have multiple machines that are identical, the same MID can be applied to multiple machines. So if you have a bank of, let's say, 6 pumps and you run 3 and 3 are spares, well, if we go out and put wireless sensors on all 6 pumps and data starts coming in from 3 every day for a period of time, and at some point in the future you switch to a spare pump, you rotate pumps, and one starts up that hasn't been running in a couple months, we have potentially 60 data sets of an identical machine to compare that to. So there's no logical reason that the data from that machine that just started up is not identical to the previous 60 data sets that we have. If it's not identical, why is it not identical? Is it a different type of motor? Is it a different number of motor bars? What's different about this motor than the other 6 or the other 5? So when we do see that there's a difference in the data, we'll oftentimes have to build a separate MID for that one machine because it is not identical to the others. But we rely on the statistical averaging with the deviation. Of course, once you get 6 or more averages built in the machine, you typically have a pretty good standard deviation. We don't like to average perfect data because you don't have much deviation. So we kind of like to, it's a work in progress. We always go back and review these averages and say, oh, well, the vibration has fluctuated slightly, so let's add a few more averages to get better standard deviation. Kind of gives you a little bit of a cushion there of a range of vibration for the machine to operate in. That way you're not getting a lot of false alerts, especially if the vibration variance might be due to some process changes. You don't want to routinely get a call every time a machine goes through a certain part of a process. Now, if it's outside, if that process change results in significant changes in vibration where it puts the vibration outside of any ISO acceptable levels, then we do not want to average that data. We never average data with a fault, but we do work with our customers. If you have a machine that the vibration sometimes does go above acceptable levels, and you're aware of that, and you're accepting of that, and you want that data to be averaged, then we typically require a management of change form. Basically, it's just you're accepting that that's outside of a normal ISO standard of vibration, and we can average that data. We can normalize it, and therefore make it a normal operating condition, so you don't get those false alerts. Several years ago, I had a customer that had some vertical lube oil pumps that were shaking well over any vibration standard. They were nearly an inch per second at rotational rate of the motor. So immediately upon startup of this program, these machines were coming in and going out as a series because at 1 inch per second, that's significant levels of vibration. But after a few months, met with the customer, we had some discussion. They knew what the issue was. The vessel that these motors were mounted on was very flimsy. The lid to the lube oil vessel was not supported very well, so it caused the motors to shake excessively. There was really nothing they could do about it. We documented that in an MOC form, sent it to the customer. The customer was accepting. They signed off on it. I averaged that data, made those machines green. Now, the great thing, or the main thing to separate here, had that been an overall alarm, and I set an overall alarm at over an inch per second, then that machine would have had to, had a bearing fault developed or looseness or any other fault developed into that machine. the overall would have had to go up so much to get an alert. Using the statistical average, because that's discrete frequency, all I did was normalize that 1x amplitude. So if in the future any looseness were to develop, that would be an exceedance from the average. It would get called immediately. If a bearing fault was to show up, that would be an exceedance of that discrete average. So we're not blind to any other faults. We're simply normalizing that specific frequency of motor rotational rate and amplitude as being normal for that particular machine. It's not very often we do that, but it does happen on occasion that a machine is just outside of any normal operating conditions. But the you see the top here, it says synthetic average. So if we do not have historical data on a machine or any historical averages, the rule base builds a synthetic average for that machine based upon the information provided. Component type, if it's a motor and a coupling and a pump, we have parts of our MID, our machine internal design template, that tells the rule base all the different components of that machine train. Is it an AC motor? Is it a DC motor? Is it on rolling element bearings? Is it on journal bearings? Is it on a VFD? How many poles? Is it a 2-pole motor, 4-pole motor, 6-pole motor? What type of coupling? Is it a flex coupling? Is it a solid coupling? Is it belt driven? All those different, and then we get to the pump. Is it an overhung pump? Is it a center hung pump? Is it rolling element bearings, etc.? All those component codes tell the rule base everything it needs to know about that machine. And from those component codes, the rule base will generate a synthetic average. So it knows what the normal expected vibration would be from that machine. So even without historical data, it can be data set number one that we get from machine. We still have a very good representation of what the data should look like. So we have that as an option of using, well, the software is going to use the synthetic average no matter what, if we don't have historical averages. Once we apply an actual average from the machine data itself, then it negates that synthetic average. And then we will continue to add averages until we get a minimum of 6 or more averages. Now, obviously, there's a point of diminishing return. We don't continue to just keep adding averages because there comes a point that you just adding an average doesn't do any more good. But the other option there would be to use the AI data lake. So based on those component codes that are described, we can search the data lake for an exact match machine. Could be, from some other industry, but that data is stored in that data lake. It can go out and fetch, based on that component code, an exact match machine and apply the averages from that machine to this machine. So theoretically, we could go out and set up a brand new customer site plant and build the machines, build the MIDs, add the component codes, and potentially add averages to machines that we've never gotten data from. So that when we flip the switch and data starts coming in, we already have these robust averages and every bit of information that we need to be very successful very early on in the process. And then, of course, the third option, as I mentioned, we can use the actual machine data. Data comes in today, we look at the data, it's good data, everything's there, it's fine, there's no faults present in the data, we average that data. Data comes in tomorrow, we review that data, looks good, we add a second average. We found that, especially for the wireless sensor, it's pretty common practice for us is that we actually apply the synthetic average. We have a process that we can actually, I said earlier, once you apply actual machine data average, it negates the synthetic average. Well, we have a process that we can actually embed the synthetic average and make that our first average, and then start adding the actual machine data averages on top of that. That really helps to improve the accuracy and negate a lot of false alarms and false calls based off of small variances in the data. The synthetic average kind of gives us a built-in cushion um, of noise floor exceedances and things like that. It just kind of really helps to reduce the false alerts. Talking about the template, the MID, plus the baseline build, we certify those MIDs. Once we get our minimum criteria met of specific machine forcing frequencies, things like pump, vane pass, motor bar. Now we do not use bearing numbers. Our software does not rely on bearing numbers whatsoever. Um, we're capable of entering the bearing numbers, and they simply put markers on the screen for visual verification. But the rule base itself does not use bearing numbers. Um, we Instead, we take the approach of telling the template or the MID everything that we can possibly know about the machine from a synchronous standpoint. If we tell it the number of pump vanes, the number of motor bars, the number of gear teeth in a gearbox, um, and we have the ability to set multiple shaft speeds within our machine. So if it's a motor belt driving a fan, then that fan is our secondary speed. So we can set that ratio between the motor and the fan to our secondary shaft speed, and then because the software then knows of those secondary shaft speeds, anything that is non-synchronous to that shaft speed by default has to be a bearing. There's really nothing else in the machine that can generate non-synchronous content. Now, obviously, cavitation, things like that will not be, I guess technically they could be non-synchronous of the impacting caused by cavitation, but it's not going to be bearing tone non-synchronous content. And the rule base does look for perceived bearing tone specifically. But the machine profile is built a conjunction of all of its components that make up a machine train. Like I said, motor, belt, fan, motor coupling, pump, all those different fluid couplings, diesel engines, turbines, thousands of different component types that we can build into the machine. Like I said, known fault frequencies we build into that template. Of course, we want the correct machine running speed. As with any vibration program, we avoid a machine that changes speed during data collection. That makes it impossible to diagnose with any system. It's very difficult to do manual analysis on a machine that is changing speeds from each location or during data collection, because what that does is actually smears your data and you don't get very discrete frequencies. You just get kind of haystacks of different content, and it makes it nearly impossible to discern the different frequencies. It just, like I said, literally smears your data. So as with any program, we want to avoid putting wireless sensors on machines that change speed during the data collection. But now if that machine is on a VFD and it changes speeds based off of a process, but the speed is pretty consistent from reading to reading, we have a process that normalizes that data, and we've proven success up to about 30% speed variance from one test to the next. In other words, from day to day or month to month or week to week, however the data is taken, our algorithms do a really good job up to about 30%. Outside of that, the machine pretty much has to be manually order normalized, so therefore automation wouldn't apply. But if it's within that 30% speed range, we do a really good job. And so that means from test to test, not during data collection. We have multiple additional processes in the back that we use. One's the MID completion score. Different aspects of the MID have a slightly different weighting scenario, where an average counts for a certain percentage of that score, whereby pump vane pass or motor bar or forcing frequencies carry a slightly different weight. So we have our minimum standards of what we want to accomplish with an MID completion score to have the template certified. and like I mentioned before, we have a very secure baseline. And for anything that's outside of that normal baseline, we often implement a management change to the customer that they acknowledge that the current condition of the machine is outside of any normal. Um, we also have within our automated process, we have what we call persistence logic. This was primarily devised specifically for around our wireless data that comes in. Because if you have a machine, I mentioned earlier, this data has to be analyzed every day, 24 hours a day, or within 24 hours every day of the year. So if we have, and I mentioned earlier, our fault rate is, serious and extreme, about 3% of the data that comes in. So if we have, 100 machines that we're looking at, and 3 of them come in a serious or extreme state, then those 3 machines have to be looked at every day by an analyst, because until they're repaired and come down out of that serious state, then we're obligated to look at that data every day. Well, if it's a persistent fault where, let's say you have a fan that's at a high level of imbalance, so that data comes in with the serious fault of fan imbalance with a recommendation to clean and or balance the fan. Well, tomorrow, until you as a customer make some corrective action, then tomorrow the analyst is going to have to look at that machine again and again the next day and again the next day. So we've developed what we call persistence logic that looks at that data, looks at the fault, the severity, looks at the analyst comments, looks at how the analyst handled that machine, and it will repeat the process. So, if data comes in today and one of my analysts signs off on that machine with, serious imbalance, here's the fault, here's the recommendations, here's what you need to do about it, and tomorrow it comes in with the exact same conditions, the exact same thing, then persistence logic will sign off on that machine for the analyst. So that removes that repetitive machine from the analyst load. And we have certain knobs and wheels that we can turn, but typically our default there is that's a 14-day occurrence. If the same fault is repetitive within the last 14 days, it will sign off on that machine. However, if there is a new fault comes in, let's say, the fan has been running for a week with serious imbalance. Well, the next day the data comes in with serious imbalance and slight bearing wear. That disqualifies the machine from persistence logic because now there is a new fault. So then the analyst goes in and looks and says, okay, now we have serious imbalance and slight bearing wear. I'm going to sign off on it. Then as long as nothing of those two change over the next 14 days, it will continue to sign off. If that slight bearing fault escalates to moderate, it gets kicked out of persistence logic. So the analyst has to review it again. So that in conjunction with automation really helps to manage the workload. We have confidence scoring. That's how confident the rule base is with the information provided, the fault forcing frequencies, the MID completion score, the accuracy of the component codes, all that comes in together for a confidence score. How confident is the automated system in these diagnostics? Profile completion scoring, and then we also have some tools in the background that are automated fault code finders. We have tools that we can run in the background that look for things like motor bar, pump vane pass. It's an algorithm that screens that data. It looks for, a peak in the high range data at 44, 48, 55, whatever potential motor bar frequencies are. It looks for those types of frequencies with side bands of 2 times AC line frequency. And if it meets that criteria, then this automated system will identify that as the appropriate forcing frequency, such as motor bar. It'll screen the data looking for common pump vane pass frequencies, 5x, 7x, 11x. It will screen that data. So we have all these tools that really help us on the back end. But this is what I mean by the confidence score and the completion profile. The confidence here is green. It's a high confidence, no warnings for this diagnostic result. And what I mean by that is if there's an odd frequency in the data that's not seen in every orientation, or high vibration in one plane versus another, or potential ski slope in the data, anything very low level vibration. Let's say if a sensor may have fallen off the machine, is laying on the ground, it's picking up some vibration but very low compared to the historical data, then that would get flagged as a low confidence. It's like we're seeing some content, but the content doesn't match our historical data, so therefore our confidence is fairly low in the accuracy of this call. And then I see that completion profile here. That's the MID completion profile. It identifies things needed such as motor bars, more averages, things like that. This is what I mentioned earlier, using those AI tools to identify the number of pump vanes in data or number of motor bars in motor data, etc. But just kind of as a quick recap here, we're getting fairly close to the end of time. We ingest the raw vibration data, whether that's from, any of multiple sources, whether that be our own products, Bentley Ranger Pro data, the Proof Technic VibGuard data ingestion, the Treon wireless sensor, Trio data, what have you. But we treat all that data the same. We review that data manually initially. We determine, well, let me back up. The Expert Alert software is going to screen that data and give us a diagnostic result. If the machine, irrelevant of what that diagnostic might be, whether it's a green machine, a slight machine, or a serious or extreme, we're going to manually review that data. We're going to make a determination of whether the pre-screen results from Expert Alert are accurate. We're going to add averages as needed. We're going to identify forcing frequencies. We're going to build these averages and get these standard deviation where we want it to be. With manual analysis plus using some of these tools and things in the background, the machine learning and AI, we're going to groom the MID or refine the MID to get it up to a level that meets our minimum criteria to certify. So that's kind of the process. The data comes in, it gets screened, we do our feature extraction. We analyze that data, we refine the MID, we build averages, and we kind of repeat this process until we get it to our minimum standard. Once it is, we certify that MID, and then it's an automated process from that point forward. If the data comes in and it's within the average plus the one standard deviation, no further screening is required because it's proven that the machine is within the average, so therefore by default it has to be good. So basically at that point, the machine results basically bypass the rule base. It gets delivered as a good machine. If there are exceedances within the data, within the average, then we do the feature extraction. In other words, each component is analyzed differently. There's a different rule base for an AC motor versus a centrifugal pump. So the data then gets extracted. The rule base runs against the motor data. The rule base runs against the coupling. The rule base runs against the pump. And all those diagnostic results are then combined back together as a report for the entire machine. So you might have a machine that could theoretically have multiple faults. You could have motor bearing wear, a coupling fault, and pump looseness. You could have those multiple different faults come out in the same machine with those diagnostics. And then those results, I said, if it meets certain criteria for automation, if it's a moderate or down, it's typically auto screened. If those results are serious or extreme, it gets kicked to the analyst for verification and review of those faults. If the analyst is in full agreement with that, he can sign off on the machine. The results are delivered out to the customer. Here's just a partial list of some of the different equipment types that our rule base is designed to work very well with. Steam turbines, gas turbines, fluid couplings, uh, all different types of pumps, compressors, shafts, proximity probes, different things. Um, One way that we do ensure consistency is our setup team has standardized a process for setting up machines. We do a plant walk down. We visually look at the machines. We review the machine list. We vet that machine list thoroughly. We ensure that the machine is a good fit for our programs. We verify operating conditions. Does the machine operate within those speed constraints that I mentioned? We record those machine profiles and we take photos when possible. Picture's worth 1,000 words. We try to embed the photos in the database if possible. Um, but we collect all this data, record it, build it into the database, and it's used every step along the way to deliver these results. But, all right, I kind of ran right up to the end here. We only have about a minute and a half left, so I will turn it back over to Robin. See if there's any questions or comments that we can get through right here at the end. And I apologize for being long-winded.
Again, thank you, Jeff, for your time. Thank you to our audience for joining us today.